Today, you're going to be working on your post lab questions and calculations for Lab 7 Calorimetry Heat of Fusion of Ice. As you're watching the video, I strongly suggest that you follow along with completing your calculations and answering your questions and pausing the video as needed to complete them. So let's take a look at what is heat of fusion. So heat of fusion is just basically describing melting or that phase change of where you're going from a solid to a liquid and how much energy is needed. So let's take a look at your observations and data that you collected from the lab. Everybody should have collected volume 1 as 100 milliliters and beginning temperature of 50 degrees Celsius as temperature 1. I was really stressing that you watched this temperature because if it was higher than 50 when you added your ice cubes, you'd end up melting too many and your volume would be higher in the end. Or if your temperature was below 50, you would not melt enough ice cubes, so your ending volume would be a little different. So, watching that beginning temperature was very, very important. Everybody's volume 2 is going to be different and temperature 1. So, volume 2 was really important that whenever you measured out that volume that you did two different measurements and added them together because we were working with 100 milliliters because that difference between volume 1 and volume 2 is going to be used in our calculations. And if your volume is higher or lower, then that's going to cause some percent error. So if you would have spilled any of your water, maybe you overflowed and forgot that you were working with 100 milliliters graduated cylinder and you had forgot that you had more than 100 milliliters of water to measure out. Or maybe whenever you were scooping your ice out, you lost some of that water. So that's going to affect some of your volume 2. So volume 2 was very, very important. Temperature 1, when I ran the lab, I was able to get my temperature down to 1 degree Celsius. So it's really important that when you're reading your thermometer, that you're trying to read it at eye level as much as possible, and that you're not reading it at an angle. Some students may not have waited long enough and to make sure that their temperature wouldn't drop any lower, so that could have caused some error. Or some students could have just thrown their ice cubes in real fast and dropped their temperature real quick, and then you didn't end up with enough change in volume in the end. That's why you're only to add a couple ice cubes at a time. So let's take a look at your calculations. So your first calculation, number 1, says using the known density of water, find the mass M1 of the original volume of water V1. So to find volume or to find the mass using the density triangle, you would see that you would multiply density times volume. So specifically, it would be times volume 1. The density of water is 1 gram per milliliter. So you could take the 1 times a 100 because that's what volume 1 was, or you could simply remember that 1 gram of water equals 100 milliliters of water. So if you have 100 milliliters of water, you have 100 grams of water because the density is 1 gram per milliliter. Question number 2. So everybody should have 100 grams for question number 1. Question number 2, you're going to find the volume of water resulting from the melting ice. So you would take your volume 2 minus volume 1 to find your volume. So volume 2 is 163, or what you got your volume. So please make sure you use your volume, your data, minus 100. So everybody will take their volume minus 100. So my difference in volume was 63 milliliters. Question or calculation number 3, find the mass M2 of the volume of water. So just like what we set up here with 1, if you have 1 gram of water, that's equal to 1 milliliter of water. So you're going to take your change in volume from number 2, and that would be 63 grams. So M2 is 63 grams. So if yours was 60 grams, or excuse me, 60 milliliters, it would be 60 grams of water. Question 4, or calculation 4, find the change in temperature of the water. So your change in temperature is going to be temperature 1 minus temperature 2. So everybody hopefully started at 50 degrees Celsius minus what temperature number 2 was. So again, use your temperature, not mine. So my change in temperature was 49 degrees Celsius. Question number 5. Find the heat loss by the original mass of water. So you're going to be using the delta Q equals mc delta T. So for this problem, can you make sure that you show your work for this particular problem here? Okay, so it says M1 specifically. So if we go back to calculation number 1, this is where we calculated M1, so 100 grams. So everybody will use 100 grams right here for M1. In the pre-lab, they specifically told us what our specific heat is, and that means that we're going to be measuring in joules. So we want to be using the 4.184 joules over grams times degrees Celsius instead of the 1 calorie. So again, we're going to use 4C, the 4.184 joules over grams times degrees Celsius, times your change in temperature. So again, your change in temperature was back here at what you calculated in number 4. So mine was 49. So your grams, they cancel out. Degrees Celsius cancels out, and you're left in joules. So this is how much heat is needed to melt 100, or that was, excuse me, this is how much heat was needed for 100 grams of water. So 21,000 joules. Calculation number 6 says to find the heat of fusion of ice. So for this one, if you could show your work, there isn't much to show here. It's going to be your delta Q divided by mass 2. So delta Q you can find up here in your calculation number 5. So whatever you got your joules to be. And I did round my number of joules to 21,000 joules. And M2, that's going to come back from calculation number 3. So whatever you got your mass from calculation number 3. So I took 21,000 joules divided by 63, and I got 333 joules per gram. So this is how much heat is needed to melt 1 gram of water. So this is your heat of fusion of ice. So that takes a lot of energy when we're working with water. Our final calculation, number 7, is where you're calculating your percent air. And it gives you the percent air formula, the true value minus the experimental value, divided by the true value times 100. And in number 7, it says the true value for the heat of fusion of ice is 336 joules per gram. So go on and take what you calculated here in number 6. That's going to be your experimental value that you plug in right here. So the true value they told you in the lab was 336. So you plug that in there, minus your experimental value. So what you calculated in number 6. So 336 minus 333 divided by 336. So the only thing that's going to look different with yours is going to be what your value is right here. So make sure you subtract, then hit enter, divided by 336, enter, times 100, and I got 0.89%. So remember, you can have a negative percent air, and the smaller your percent air, the more accurate you were with your lab in taking your measurements, and you had really good lab techniques. So that's really well. If you had a larger percent air, at the beginning of the video, I kind of described some ways that could have caused some percent air. So let's move on to question number one. Question number one says, list possible sources of air in this experiment and how might the use of the calorimeter, such as the one shown in figure 7-1, reduce some of these errors? So like I mentioned, we've discussed some of those errors also in pre-lab. We discussed them going in. The calorimeter, or figure 7-1, is the picture of the calorimeter in your pre-lab discussion page. So kind of look at that calorimeter to see of ways that you could improve your styrofoam cup setup. Okay, so how you can make improvements to that for the second part of the question. Question number two. One source of air is the flow of heat between the water in the cup and the surroundings. Explain how this air is reduced by starting with water at about 50 degrees Celsius. So let's go on and discuss this answer together. Okay, so room temperature is about 20 degrees Celsius. And we were heating our water to to 50 degrees Celsius. So from 50 degrees Celsius to around 20, because our rooms may not be exactly 20. They could have been a little bit warmer since we've ran the Bunsen burners and had several bodies in there producing heat. So the water could have been a little bit, or the room could have been a little bit warmer than 20 degrees Celsius. So from 50 degrees Celsius to room temperature, the heat that was being used to melt the ice, that warm water, was actually escaping the cup. It wasn't going into to melt the ice. It was leaving the cup into the room. However, once the water temperature reached room temperature or below it, that's when you had a change in heat flow. It reversed. So the heat was no longer flowing from the warm water that was in your cup out into the classroom. You could feel the warmth, but once you reached room temperature, it started to feel cool at that point. And that meant that the water or the heat was flowing from the water into the ice. So basically, these two heat flows or effects canceled each other out. So question number 3, I would like for you to also answer on your own. In what way does calorimetry make use of the law of conservation of energy? So we discussed the law of conservation of energy in our notes, saying that heat cannot be created or destroyed. It just changes forms. So think about kind of our lab technique. Think about where the heat was flowing and what the purpose of this particular lab or why the heat was needed when answering your question for number 3. I would like for you to also answer number 4 on your own. Basically, you have 4 terms there that you are going to define. We've discussed 3 of the 4 terms. The term C, heat of fusion, I mentioned in the video, but if you look back in the pre-lab discussion, it also discusses these terms too. Question number 5, it says, is the process of melting exothermic or endothermic? And give evidence to support your answer. So what I would like for you to do is think about, especially in question number 2, if this was exothermic or endothermic. So which way was the heat going in or out to melt the ice, and why you feel that way. Question number 6. What is the difference between heat and temperature? So, heat is a form of energy or a type of energy, and temperature is going to be a means to measure your heat. So, we're specifically measuring the kinetic energy or the movement of your particles that are within your substance. So, let's take a look at question number 7. And no, before I move on, you do not have to write a lab conclusion. You just need to finish the post lab questions. That's it. So, question number 7 states try this problem in calorimetry. A solid substance with a mass of 200 grams is at a melting point temperature in a calorimeter. While the substance changes from a solid to a liquid at the same temperature, the 400-gram mass of water in the calorimeter goes from initial temperature of 80 degrees Celsius to the final temperature of 30 degrees Celsius. So, A, how much heat did the water lose while the substance melted? So, you're going to want to use this formula here. Delta Q equals mc delta T. And I will tell you that there are two masses that are stated in this problem. However, when you're working with the calorimeter, remember we're taking the temperature of the water, not the temperature of your substance. So you want to make sure you're using the mass of the water for M, not the mass of your substance that you're melting. C, we're going to use the 4.184 joules over grams times degrees Celsius for C. And delta T, remember that's going to be your final temperature minus your beginning temperature. Okay, so that is going to be for A. Now for B, what is the heat of fusion of the substance that melted? So here's your formula that you're going to use to find your heat of fusion here. So delta Q is what you get for your answer here, divided by the mass of the solid. So that's where you need to know or use the mass of your substance that you were melting. That goes in down here, not the mass of the water. And that will be joules per gram.